and welcome our last lesson. This is our last revision lesson for physics. So welcome. For those who are present during the previous lesson, we actually introduced uniform circular motion. We looked at some terms. Some of them are angular displacement. We also looked at angular velocity. We looked at some formulas that we use for angular velocity. We talked about centripetal acceleration and also centripetal force. So after that, we looked at some case examples. For example, a car rounding a bend, where we discussed banking of roads and also the car moving on a flat surface. Then we also looked at some examples on involving the same, and we started by discussing vertical circular motion, where I think I developed a technical problem and I was not able to finish the derivation of those formula for tension in vertical motion. So that's where we're going to pick up from. When you talk about vertical motion, we are talking about this first. On your screen on the left, you can see the first diagram here. It's a photo showing a roundabout that is moving in circular motion. So remember, we have two types of circular motion. We have this vertical one, and we have horizontal, like the way this person here is actually spinning something like a stone that is tied on a string. So this is horizontal circular motion. And on the left, we have vertical circular motion. So when we talk about tension at the upper part here, not being equal to tension at the lower part here, is because of the force of gravity, which is acting on the bodies as they move, which is also not the same as tension on the left at this region, and also not the same as tension on the right. When it comes to horizontal circular motion, like the second case here, where the stone is being whirled horizontally in a circle, then we assume, actually we don't assume, but the fact is the acceleration due to gravity of this stone is acting downwards. Therefore, it has nothing to do with the centripetal force, which is in the string here, the tension in the string. So we ignore it. So anytime you see vertical motion, vertical circular motion, then you have to introduce the issue of weight of that object, which affects the centripetal force, like in this case. Whenever you see horizontal circular motion, like in this case, then you neglect the weight of this object, which does not affect the tension in the string that provides for centripetal force. So maybe quickly we can proceed from where we stopped. It was at this point, motion in a vertical path. And we said that the tension at the top here, when this stone is at the top here, then the tension is the least. And tension at the bottom here is the highest, because you can see this is mv squared over r plus mg, while at the top here it is mv squared over r minus mg. So this definitely is higher than this. Tension on the sides at C and D, we can see that mg has neither been added nor minused. Therefore, the tension in the string remains mv squared over r, both at C and at D. So I was now at that point where I think I got lost online. I was trying to explain how do we come up with minus mg and plus mg. So let's start with that point A. At point A, we can see that there are two forces acting on the stone. And the two forces are acting in the same direction, which is towards the center of the circle. So one of them is weight, and the other one is tension. So these two forces are the ones that they're the ones that bring about the centripetal force, so that that stone is maintained in that circular motion. So we can now say that centripetal force FC, F subscript C, is equal to tension T plus weight, because we can see they are acting in the same direction, therefore we add. So using the physics symbols, Fc equals to T plus W. Then Fc, previously we learned that Fc represents centripetal force. I think at some point here, we were able to see that centripetal force is mv squared over r. So we substitute where there is Fc, we put mv squared over r equals to tension T plus weight is mg. The weight is mg. Therefore, by making T the subject, capital T equals to mv squared over r minus mg. So that's why at point A, we have tension equals to mv squared over r minus mg. Let's go to point B at the lower point. This point over here. We still have the two forces acting on the ball. The weight, we can see the red line showing weight, which acts downwards, and the tension, which acts towards the center of the circle. So the two are opposing each other. So because the two are the ones contributing to the centripetal force, we can now say that Fc, which is the net force or resultant force, equals to tension towards the center minus weight W, because they are opposing each other. So this gives us the resultant force. Using the physics symbols, mv squared over r equals to tension T minus mg. Therefore, T equals to mv squared over r plus mg. So the total tension at B becomes mv squared over r plus mg. That's why we have this equation here. Then at point C and D, this stone experiences centripetal force which is not affected by the weight of the stone. Therefore, we ignore mg, because you can see the stone's weight acts downwards on the left and downwards on the right. So the only force that is available here is tension. Therefore, centripetal force Fc equals to T. And therefore, T is mv squared over R. So that's why we come up with those four equations. Before applications, I want us to look at some examples. So I'll share some questions. Unless there is a question, if you have a question, raise your hand up. In the meantime, let me share the questions. So we have some questions here, which are normally set from this chapter. I think you can see them on your screen. So question number 1 says, define angular displacement. Angular displacement denoted by theta. So the answer is, this is the angle subtended at the center of the circle when the body moves around a circular path. Angle subtended at the center of the circle when the body moves around a circular path. Define a radian. A radian is the angle subtended at the center of the circle when the arc length covered by a body equals to the radius of that circle. So when the radius of the circle equals to the arc length, then the angle at the center of the circle is a radian. Centripetal force, this is a force that acts on a body towards the center of a circular path to maintain its circular motion. Angular velocity is the rate of change of angular displacement. SI unit is radians per second, written as rad per second. Distinguish between linear velocity and angular velocity. Distinguish means you give the definitions. So linear velocity is the rate of change of linear displacement, while angular velocity is the rate of change of angular displacement. Then we have state what is meant by centripetal acceleration. This is the rate of change of angular velocity. Define critical speed. We said that critical speed is normally at the corners of a road, sometimes on a banked road. And this is the maximum speed beyond which the car skids off the road. Maximum speed beyond which the car skids off the road. Explain why bodies in circular motion undergo acceleration even when their speed is constant. We said that usually bodies in circular motion have a constant linear speed, but the reason why we say they are accelerating is because those instantaneous speeds are in different directions. So the answer is this is due to the constant change in direction, hence change in velocity. So it's the direction that makes us say they are accelerating. Number 9, explain why the moon is said to be accelerating when revolving around the Earth at constant speed is the same. We say the moon is constantly changing direction, hence change in velocity. State 2 ways in which the centripetal force on the ball in its circular motion will be reduced. A ball rotating in circular motion. So this is asking you about factors affecting the centripetal force. And we have 3 of them. One of them is mass. So for us to reduce the centripetal force, we reduce the mass of the ball. We can deflect it to some percentage. Number 2 is the angular velocity. So for us to reduce the centripetal force, then we can reduce the linear velocity, which in turn reduces angular velocity. And the last one is we reduce the radius of the bend of that circle. I think there are ways of reducing that radius. What is meant by the term banking in roads? Banking is raising of one side of the road, starting from the inner side to the outer side, to make it assume a saucer, S-A-U-C-E-R, to make it assume a saucer-like shape. Saucer-like shape. Raising of one side of the road, starting from the innermost to the outer side, making it assume a saucer-like shape. That's the banking. State 2 factors which determine the maximum speed at which a car can successfully negotiate a corner on a banked road. So this is testing on what are the factors affecting the critical speed, because this maximum speed is critical speed. So that speed V equals to the square root of RG tan theta. Square root of RG tan theta. So we have 3 factors. One is radius of that road, that bend. Number 2 is the angle of banking of that road. And number 3, the nature of tires and the road. If the tires are worn out, of course, the speed has to be very low. Friction will be low. State the condition necessary for a car traveling on a banked road not to skid. Of course, it's the same question, asking about the factors affecting centripetal force. I think we have a question. Somebody viral. I can't see you again. You have disappeared. Okay, we will respond when he comes back. Let's proceed. State the condition necessary for a car traveling on a banked road not to skid. Of course, here we can talk about reduction of speed, which will in turn reduce, it will reduce the critical. When we reduce the speed, then we are actually making the car require the least amount of centripetal force for it to maintain that force, that circular track. If we increase the speed beyond critical speed, then it's going to skid. We can also ensure that the tires are very rough. They are treaded so as to increase friction, which provides for centripetal force. Explain why a pail of water can be swung in a vertical circle without the water pouring out. Here, you see the water is acting in the opposite direction to the centripetal force. So the bucket exerts a centripetal force on the water towards the center of the circle, making it not to pour out. State the reason why banking of a circular part of the road is necessary. I think those are repetition questions. Let's go to calculation. So let's look at question number, before we look at calculation, number 26. The figure below shows masses A, B, and C placed at different points on a rotating table. The angular velocity of the table can be varied. So you can see A is innermost, followed by B, then C. So one says state two factors that determine whether a particular mass slides off the table or not. So this is testing on the factors affecting centripetal force. So we can talk about roughness of the ball and nature of the surface of the table. That is one. Number two is the masses of the of those. Just say they are masses. It is found that masses slide off at angular velocities A, B, and C. I think there's a. It's found that masses slide off at angular velocities A, B, and C of decreasing order. So C slides off first, then B, then A. I think the question is supposed to be explained. So of course, since they have different radius, A has the least, followed by B. C has the highest radius. And we know that increase in radius leads to decrease in centripetal force required. Therefore, C, suppose now they are revolving at the same speed. Remember here the speed is the same. Therefore, the experience, C will need more centripetal force to maintain that track. A requires the least centripetal force to retain that circular path. So, as you explained, mention the amount of centripetal force required due to the difference in radius. 27 is I think some experiment there. Let's look at question 1. The figure below shows a bucket filled with water of mass 5 kilograms. tied to a string 3.6 meters long and being rotated in a vertical circle with a constant speed of v meters per second. Write an expression for this minimum force experienced. So minimum force experienced is at point A, and that force, we said it's tension force given by T equals to mv squared over r minus mg. So it's the tension force given by mv squared over r minus mg. Part B, use your expression to determine the value of V. So we are looking for V, and we are told that it's a bucket filled with water of mass 5 kgs, radius is 3.6, being rotated in a vertical circle with a constant speed of V. So substituting here, we have tension. So the tension here is not given. Suppose we assume that the tension is the same as this mass here times acceleration due to gravity, then we will have 50 equals to 5 times v squared over radius 3.6 minus 5 times 10. So that will give us v will be 0. I think there's a problem with this question. The tension has not been provided. So question A has an issue. B, use your expression. That one we've talked about. C, calculate the minimum speed the bucket takes to rotate in position A so that the water remains in the bucket. The same we will need tension. Let's look at B at question 2. A stone of mass 450 grams is rotated in a vertical circle at 3 revolutions per second. If the string has a length of 1.5 meters, determine the linear velocity. So here we are supposed to look at linear velocity, and we know that omega, which is angular velocity, omega equals to v over r. Therefore, v is omega r, and omega is this one here, 2 pi f. We have f, 3 revolutions per second is the same as frequency. So 2 times pi times 3 gives us omega, multiplied by radius 1.5. So here, from the calculator, we get 2 times pi times 3 times 1.5. The answer is 28.27 meters per second. Roman 2, the tension of the string at positions A and B. So tension at A, which is the uppermost part, TA, equals to mv squared over r minus mg. So substituting 0.45, which is the mass, times v squared, which is 28.27 squared, over r 1.5. Everything subtract mass, which is 0.45 times 10. So 0.45 multiplied by 28.27 squared divided by 1.5 gives us 239.76 minus 4.5. So when we minus 4.5, we get the answer is 235.26. That's the answer. Newtons. Tension at B, we add. So T at B equals to mv squared over r plus mg. So that will be, when you do mv squared over r, gives you 239.76 plus 4.5. So 239.76 plus 4.5 gives us 244.26 newtons. So the tension at B is higher than tension at A. We have so many questions revolving around that formula, mv squared over r. Like question 4, a particle revolves at 4 has in a circle of radius 7 centimeters. Calculate its linear speed. So first of all, we are supposed to get omega, which is angular velocity. So you say angular velocity omega equals to 2 pi f. So 2 times pi times frequency is 4. Whenever you see revolutions per second, it's the same as has. So 2 times pi times 4 gives us 25.13 radians per second. Then we come and say, but omega equals to v over r. So v equals to omega r. That gives us 25.13 times radius, 0.07. The answer is 1.759 meters per second. That's the linear speed. Angular velocity, we have already calculated 25.13 radians per second. Question number 5. A 150 mass tied to a string is being whirled in a vertical circle of radius 30 centimeters with uniform speed. At the lowest position, the tension in the string is 9.5 newtons. Calculate 1, the speed of the mass. So at the lowermost point, tension is given by T equals to mv squared over r plus mg, because this is a vertical circle. Substituting, tension is 9.5, mass m 0.15, v is what we are looking for, times v squared. Radius is 0.3 meters plus 0.15 times 10. So 9.5 equals to, when we simplify, we have 0.15 divided by 0.3 gives us 0.5 v squared plus 1.5. So 0.5 v squared equals to 8. So v squared is 16 and v is 4 meters per second. Roman 2 is asking for the tension in the string when the mass is at the uppermost position of the circular path. So uppermost position we minus. So T equals to mv squared over r minus mg. Therefore, T equals to m is 0.15 times 4 squared over 0.3. We are using 4 because the linear velocity doesn't change throughout the circle, minus the mass is 0.15 times 10. So this gives us 0.15 times 16 divided by 0.3. We get 8 minus 1.5. The answer is 6.5 newtons. So the uppermost part has a tension of 6.5 newtons. We can do 6 and 7, then look at a graph. So question 6. A stone 0.5 kilograms was tied to a string that was 120 centimeters long and whirled in a horizontal circle at the rate of 150 revolutions per minute. Remember, this is a horizontal circle, so mg is out of the question. As long as it's horizontal circle, you ignore mg. So 120 centimeter, 150 revolutions per minute is the frequency. So you convert to revolutions per second, which is the same as hertz. So you say 150 revolutions are in 60 seconds. So how many will be in 1 second? That gives us frequency. So 1 over 60 times 150 gives us 2.5 hertz. So 150 revolutions per minute is the same as saying 2 hertz. 2.5 hertz or 2.5 revolutions per second. Therefore, we know from waves that t equals to 1 over f. Therefore, the periodic time t is 1 over 2.5, which gives us 0.4 seconds. That's the periodic time. Then Roman 2 is determine the angular velocity omega. So omega equals to, you have two options. You can use 2 pi f, or you can use 2 pi over t. Either 2 pi f or 2 pi over t. So 2 times pi divided by 0.4. Let's see what we get. 2 times pi equals to 6.283. Answer divided by 0.4. We get 15.71 radians per second. 15.71 radians per second. Maybe for you to practice, let me give you 4 minutes. Attempt question number 7. Then we can have somebody explain briefly, maybe in 2 minutes. Then we look at a graph. So it's 11:43. Let's look at the answers at 11:47. Okay. I hope we have attempted the question. Question number 7. Anyone to present 7 Roman 1 periodic time? Yes, we have EW. EW, I don't know the full name. Can go on. Yes.
0.2 seconds.
0.2 seconds. Explain which formula?
So periodic time is equals to 1 over f, which is frequency f. So 1 over 5 is equals to
Correct.
0.2 seconds.
Yes, thank you for that correct answer. So we are told it is swung vertically at 5 revolutions per second. That is the same as frequency. So periodic time T is 1 over F. You write that equation because it has a mark. Then substitute 1 over 5. The answer is 0.2. Angular velocity, omega. We can hear from Quincy.
Okay, from the two formulas, we have
Yes.
2 theta. No, 2 pi over t, and the other one is 2 pi f. So since we have periodic time and we also have frequency, we go for periodic time since tumeshaipata, of which 2 pi over 0.2 itakupatia 31.42.
Correct. Radians per second. Correct. Thank you for that correct answer. Let's have explanation to Roman 3. Roman 3. Yes, you can go on, Quincy.
Okay, for linear velocity, remember the formula. V is equals to omega times R. Okay.
Yes.
We have already found omega, which is angular velocity, and radius, I think it's 70 centimeters, which is 0.7.
Correct.
So V
0.7.
So V
Continue.
V is equals to 31.42 times 0.7. But here,
yes. Yes.
But here 21.994 meters per second.
Correct. Thank you very much for that answer. You can finish Roman 4 because you have the values for 1, 2, 3. Maximum tension.
Maximum tension.
Yes.
Okay. It happens when the lead shot is at its lowest point. So using the formula, T is equals to mv squared over R plus mg. We substitute. T is equals to, the mass should be in kilograms. So it's 0.04.
Yes.
Times 21.994 squared over R, which is 0.7.
Yes.
Plus mg. Mg, our m is 0.04. Then our g is 10.
Correct.
So let's work out. 0.0. Yes. And our answer is 28.042.
Correct, 28.042.
Okay, the units should be, since it's tension,
Yeah.
it should be kindly inside here for you. G units.
Tension is a force.
So it is in newtons.
Newtons, yes.
Okay.
Thank you. Thank you for that good presentation. We proceed. Now we have questions that come in form of graphs or linear motion can be combined with circular motion. For example, number 25 on our screen. It's a combination of linear motion and circular motion. The diagram below shows a mass M, which is rotated in a vertical circle. The speed of the mass is gradually increased until the string breaks. The string breaks when the mass is at its lowest position, A. I think A is missing there, but it's supposed to be at the same lowest point here. And the speed was 30 meters per second. That is linear speed V. Point A is 5 meters above the ground. You can see 5 meters. So A, show on the diagram the initial direction of the mass at the point the string breaks. So when you're asked to show the direction, then you are supposed to put a tangent. In maths, we learn about tangents. These are straight lines that touch the circle at only one position. So you will put a ruler over here, horizontally, this way. Then you draw a straight line, either pointing to the right here or straight line pointing to the left, because the question has not told us whether the revolution is clockwise or anti-clockwise. So just draw a line coming from point A to the right and put an arrow to show that when the string cuts, then the mass moves this direction on a straight line. Because remember, it has velocity, and velocity is a vector quantity. That's why we are using a ruler. Okay. Roman 2. Show on the diagram the path of the mass from A until it strikes the ground at point B. So if you can remember, we learned about the projectile motion. So when the string breaks, the mass follows the arrow you initially drew. It goes as it moves down and strikes the ground at a certain point, anywhere on this ground. So you will draw what you call a trajectory. I think we've heard about a trajectory. If you can remember the projectile motion very well, it moves through that trajectory and strikes the ground at point B. Part B of the question, calculate the time the mass takes to reach the ground after breaking off. So, from projectile motion, we learned about height, h, which has been given as 5 meters. So, we can say that h equals to a half gt squared. h equals to a half gt squared. Therefore, 5 meters equals to a half times 10 times t squared. When you divide, you find that t squared equals to 1. Therefore, t is 1 second. So that ball, that mass is going to move 1 second, then it strikes the ground. B Roman 2, the horizontal distance the mass travels before it strikes the ground. So we are being told from this point to where it strikes the ground, what is the range? So your range will be R equals to UT. R equals to UT, and our U is 30 meters per second, which is given up there, times time 1 second. So the answer is 30 meters. Roman 3, calculate the vertical velocity with which the mass strikes the ground. So vertical velocity, we can use the first equation, which says V equals to U plus GT. V equals to U plus GT. Remember, this is vertical motion. That's why we are being told vertical velocity. Substituting, U equals to 0 plus G we know is 10, time taken is 1. So the answer is 10 meters per second. So the ball, this mass strikes the ground at 10 meters per second. Remember, in vertical motion on a projectile trajectory, we assume that the initial velocity was 0, vertically 0. It's the horizontal velocity that is never 0. So this is a combination of linear motion and projectile, circular motion. Number 26 is another application question. A child of mass 20 kilograms sits on a swing of length 4 meters and swings through a vertical height of 0.9 meters as shown below. Determine the speed of the child when passing through the lowest point. So for us to find the speed, which is linear speed, remember this child is tracing an arc length of a circle. So the circle is supposed to be round that way, but he's only tracing a small portion of it. Therefore, potential energy lost equals to kinetic energy gained. So you say PE lost equals to KE gained. Substituting, we have mgh equals to a half mv squared. The mass of the child doesn't change, so we can ignore it, both sides. So gh equals to a half v squared. G is 10, h is 0.9, equals to a half times v squared. Therefore, v squared equals to, that is 9 times 2, 18. And the velocity will be the root of 18. Square root of 18 gives us 4.243 meters per second. Then determine the force exerted on the child by the seat. We have a question. Nodding. Go on.
Or for the height of the GH, we'll use the 4 or the 9, 0.9.
We use 0.9 because initially, where is the child? The child is at 0.9 up. but the lowermost point is over here, down here. So the child is going to lose a height of 0.9, not 4. If he was seated up here, then we can use 4. But he's seated down here on a level of 0.9 from the bottommost part. Sawa?
Sawa.
Yeah. Any other question? Okay, let's proceed for question 2. The force exerted, we know, is the same as tension in the string, which is mv squared over r plus mg. mv squared over r plus mg. So the mass is 20. Velocity 4.243 squared. Radius is 4 meters plus 20 multiplied by 10. So working out, we have 4 multiplied by, 5 times 4.243 squared plus 200. So I'm getting 290.02 newtons. So that's the force exerted by the seat on the child. So it's just an application of circular motion in a different way. Now we have these questions. Graphs. Because remember, graphs are also set in theory. You can be drawn for the graph, and then you are asked to answer the questions that follow. So the graph below was obtained when an experiment to investigate the variation of centripetal force F with radius r of the circle on which the body rotates was performed. So I think we can see the values are very clear. We have force, newtons, radius, meters. From the graph, determine the angular velocity, omega, of the body, given that mass m equals to 100 grams. And the formula is given as F equals to m omega squared r plus c, where c is a constant. So this is the formula that represents this straight line. And we know that in maths, all straight lines have their equation in form of y equals to mx plus c. So you're going to find out from this equation given, what is y, what is m, what is x, and what is c. So you can write the two formulas down, F equals to m omega squared r plus c. Underneath that equation, write y equals to mx plus c. So we are going to cancel what represents y. So on y equals to mx plus c, we cancel y. On the formula F equals to m omega squared r plus c, we cancel F because we can see on y-axis, we have F. On x-axis, we have R. The quantity is R. So cancel R. And on the mathematical equation mx plus c, you cancel x-axis, x. So what we are left with is m. And what we are left with on this equation is m omega squared. Therefore, we can now conclude and say that the gradient equals to, or the slope equals to m omega squared. You can pick a question from Austin. Yes, Austin. Yes.
Ukiamka kwenda church, mwamka kuvuta bangi. Kuvuta bangi ndo ni dili na mashetani. Kukula bangi zishike zikiwa ndani, na kama hupendi bangi wewe ni mtoto wa shetani.
Austin Isinta, that one is discipline. And I think we will follow up on that. Okay, so we've seen that gradient equals to m omega squared. Therefore, we look for the gradient in on this line. So you select points which are clear and they can give you the slope without a hassle. I can see a point like 0.2 and 0.25. The coordinate 0.2, 0.25 is very clear. So 0.2, 0.25. Another coordinate which is clear, I can see 0.5 and 0.6. So 0.5, 0.6. Now we say that the slope equals to change in F over change in R. Substituting, we have 0.5, 0.6 minus 0.25, everything over 0.5 minus 0.2. So we get 0.6 minus 0.25 gives us 0.35 over 0.3. 0.35 divided by 0.3 gives us the answer as 1.167. That is the slope. Then we come back and say that slope, since we said that the slope equals to m omega squared, therefore we can conclude and say that 1.167 equals to mass, which has been given down here. You can see 100 grams. 100 grams is the same as 0.1 kilograms multiplied by omega squared. Therefore, omega squared equals to 11.67. So you square root 11.67 and we get the answer is 3.416 radians per second. 3.416 radians per second. So this is how you can interpret a graph which has been drawn from uniform circular motion. Remember, you can also be given values to draw the graph and use the graph. There is an equation down here that says T equals to m omega squared over R minus C. Use it to find the constant C and the mass m. So you follow the same process. You know y-axis is T, x-axis is angular velocity. So you cancel angular velocity squared and x. So you remain with mr. mr is your slope. And negative c is y-intercept. That's how you interpret the graph. Okay, back to applications. Applications, we have number one, centrifuges. And during the introduction of this topic, I said that A centrifuge is a device or a machine that is used to separate milk and ghee. So milk is put in those containers and then it's revolved so many times at a very high speed. Because milk is a mixture of different particles, we have the liquid part and the solid part, which is ghee now. The solid part will require a higher centripetal force, but the liquid particles will require a lower centripetal force. So at the end, we have the solid part moving away from the center. They gain more radius than the liquid part. And that's how we separate the two. Application number 2, circular motion is used to construct merry-go-round and roller coasters used in entertainment. So nobody just wakes up and constructs these things. A lot of measurement in terms of capacity, what is the maximum mass it can hold at the bottom part here? What is the minimum tension here for them to come up with that structure? Otherwise, it can cause serious accidents. The same as roller coasters, you can see those curves have to be measured. Here we have satellite, launching of satellites to space. These are communication tools. You can use them for communication using satellite phones. You can also use satellite internet. So they receive information from the Earth and relay the same information to a different position. And many countries have launched the satellite to space for their own use. So the equation that relates the satellite and the Earth, which combines the two, is here, where m1 is mass of the Earth and small m is mass of the satellite. So the centripetal force F experienced by the satellite is given by G capital, not small. This capital G stands for universal gravitational constant, which is not 10, something else. Multiply by mass of the Earth, multiply by mass of the satellite, divided by distance between them, squared. R stands for distance between the satellite and the Earth, squared. Therefore, we know that the centripetal force is given by mv squared over r, and the same centripetal force is gm1 m over r squared. We can cancel now. This is mass of the satellite, cancels out. Then we make v the subject of the formula. So the velocity of the satellite will be given by the root of gm, mass of the Earth, over r. So this is just for your own personal knowledge. So the only question that comes from here is state 2 applications of uniform circular motion. Then you can talk about satellites, talk about merry-go-round, talk about centrifuges, and so on. So that marks the end of the lesson today. Unless there is a question, we still have a few minutes. You can raise up your hand. But if there's no question, you are free to leave. And have a happy new 2025. And also Merry Christmas. We meet next year. If anyone has a question, you have around 10 minutes. You can talk about your question. Yes, Eric Kibet. Yes. Eric. I can't hear you very well. Louder.
Kesho tuko na subject gani?
Sijui, unless tomorrow is on Saturday.
Yes.
You can consult Mr. Omarwa. He's the one coordinating. So he will be able to inform you, sawa, through the parent.
Sawa.
So I think there are no more questions. Let's stop there.